All right, welcome back, everybody. We are going to keep plugging on in Chapter 9. Like I said last time, we're about to get into the meat of reaction chemistry here. So we're about to get heavy duty into some reaction mechanisms. So definitely be on top of things as you're going through these and do a lot of practice. You're going to see that reactions of alcohols are plentiful. There's a lot that you can do with alcohol. So that's where we're going to start. It's going to be reactions of alcohols. Now, we're going to see that with alcohols, just like with alkyl halides, we can get SN1, SN2, E1, and E2 reactions. However, things are going to be a little bit different. For one thing, in these reactions, we always have leaving groups, right? So we saw in the last couple of chapters that our leaving groups are halides. Cl-, Br-, etc. These are all good leaving groups because they're weakly basic, right? We learned that the weaker the base, the better the leaving group. Alcohols, in and of themselves, do not have good leaving groups. Take a look what the leaving group is going to be. Basically, what you do in a reaction of an alcohol is you get rid of the OH group. So, if this just left by itself, that would give you OH minus as a leaving group. Well, what is OH minus? You guys know this. You've seen this since high school. OH minus is the hydroxide ion. What do you know about the basicity of a hydroxide ion? Yeah, it's a strong base. And that means it's a terrible leaving group. Not good at all. Alright? So you may think, okay, well, how can alcohols even be able to do SN1, SN2, E1, E2 if we have a bad leaving group? An inherent part of all of these reactions, because it's going to be sort of doing a preparatory step. Before we even get to the SN1, SN2, E1, or E2, there's a preparatory step where we take the bad leaving group OH and turn it into something that is a good leaving group. And then we can actually proceed with the desired reaction. Okay? So that's something that's a little bit different than the last couple of chapters, is we have to turn a bad leaving group into a good one. And there's a few different ways of doing that. Sorry, I have the hiccups, so please forgive me if I have an awkward pause. There's a few different ways of doing that. The most common way of doing it is to simply take your OH, add a proton to it, and turn it into water. Water, as you guys know, is very, very weak. Is a very weak base, so that means it makes an excellent leaving group. And we can see an example of that with our first set of reactions. We're going to look at dehydration of alcohols with strong acids. And these are going to be specific strong acids. There's a few different ones that you can use. There's going to be two in particular that we're going to be focusing on with these reactions. One of them you're probably very well familiar with. H2SO4, right? You guys know that's sulfuric acid. So you can use that acid, or you can use one called TSOH. This is short for para-toluene sulfonic acid. Now, that's a bit of a wordy name. If you look at the structure, it's also, not really simple either. It looks like this. So you can kind of see why we use the abbreviation TSOH. It's a lot simpler. But basically, this proton right here is very, very acidic. So this proton can be given off and donated very easily. TSOH and H2SO4 have approximately the same acidities. They're both very strong acids. They can basically be used interchangeably in these reactions. So sometimes I'll use H2SO4, sometimes I'll use TSOH. Just depends. They both serve the same purpose. All right? So let's take a look at an example. First of all, before we get to the specific mechanisms, let me show you generally what happens. Regardless of which mechanism you use, and it's going to be either E1 or E2, because this is an elimination reaction. Dehydration, what does that kind of bring to mind? Kind of brings to mind losing water, right? And that's basically what you do. You take your alcohol, you add either sulfuric or paratoluene sulfonic. I'll just use sulfuric here. And basically what that does is it produces an alkene and gives you water as a byproduct. And if you look at what is given up by the alcohol, basically what happens here is that one carbon loses an OH minus, and another carbon loses a beta hydrogen. Yeah. Remember how we said in elimination reactions in Chapter 8, the carbon with the Cl or the Br or whatever, that was the alpha carbon. In this case, with alcohols, that's going to be the alpha carbon, the one with the OH, and adjacent carbons are going to be beta. And just like before, beta carbons can also have beta hydrogens. All right? So you lose an OH minus and you lose an H plus for an overall loss of water. And in the process, you make an alkene. Okay? So you could have something like this. Just like we saw with elimination reactions of alkyl halides, you can have mixes of alkene products. Yay, mixes. Nice and complex, right? If you had something like this, right? You see, well, what's different about this example as opposed to the other one? We actually have beta hydrogens on this carbon and on this carbon. So we have two different types of beta hydrogen. So you could form a double bond between those two carbons, or you could form a double bond between those two carbons. So yeah, just like we saw in the last chapter, you can also get mixtures of alkene products with eliminations of alcohols. Do you see anything else we should have here? Oh, excellent catch. Good eye. You notice that we have a trans product here. If we have the trans, that means we can also have the cis, just like we saw in the last chapter. Okay? So that is something that we have to keep in mind. Now, that being said, depending on the mechanism that we use, our life can be a little bit simpler or it can be a little bit more complex. It just kind of depends. All right? Just like with alkyl halides, these eliminations can undergo by either E1 or E2 mechanisms. Now, the rules, though, the requirements are going to be different. You saw in the last couple of chapters we had a list of items. We had alkyl halide, we had strength of the nucleophile base, and then we had the type of solvent. You kind of use the preferences of those to figure out which mechanism or mechanisms you have. Here it's actually a little bit more cut and dried. All right, I'm going to start off with the E2 mechanism. You get the E2 mechanism in dehydration of alcohols only with primary alcohols. That's it. If you have a primary alcohol, you're dehydrating it with an acid, it's going to be E2. And these tend to be simpler because since these can only happen with primary alcohols, you're not going to have multiple types of beta hydrogen. So your products are actually pretty simple. You don't get product mixtures with these. I didn't draw this very well. Let me draw it again. There we go. That's a little bit better. Okay? I'll use TSOH just to make sure I'm not leaning too much on sulfuric acid. Okay. All right. So the first step, before we even get to the elimination, remember we have to prepare the OH. We got to turn it from a bad leaving group into a good leaving group. We have a strong acid, right? What do strong acids like to do? They like to give up protons. Well, the proton needs somewhere to go. Fortunately, the oxygen in your alcohol has free electron pairs. So basically what happens is that alcohol can pluck off an H plus from your acid, and lo and behold, we don't have an OH group there anymore. We have water hanging off. And water is an excellent leaving group. So it's going to leave. And since this is an E2 mechanism, that means everything else from this point happens at once. So that means we're also going to be losing a beta hydrogen here at the same time your water leaves. What acts as the base? Well, what did you have left over once you lost the hydrogen from TSOH? Yeah, you had TSO minus left over. This actually acts as the base that can grab your beta hydrogen, and this pair of electrons falls. Oops! Oh, crud. I drew the beta hydrogen in the wrong spot. How embarrassing. My bad. The beta hydrogen's actually right here. Sorry about that. So your TSO minus grabs this guy. These electrons fall into a double bond here, and your water is kicked off. And that means you get this alkene, and that's the only alkene that you get. You get water as a byproduct. You end up regenerating your TSOH, so that's basically means it's going to be acting as a catalyst in this reaction. Okay? And so yeah, if you think about it, if this only works with primary alcohols, I mean, there's really not any situations where you can get multiple types of beta hydrogens. You're really only going to be making these types of alkenes, so you're not going to have cis or trans or E or Z or anything like that. So these are nice and simple. These are pretty easy to deal with. Okay? Where it gets a little bit more complicated is with your E1s. Those are definitely more involved. Well, let's take a look at your E1s. Alright. Now E1s, as you might suspect, since E2s only worked with primaries, these are going to be what secondary and tertiary alcohols do. Alright? No matter what, if you have a secondary alcohol or a tertiary, you do a dehydration, it is going to undergo an E1 mechanism. Alright? So let's take a look here. Alright, let's say we had this guy. Let's use a tertiary. Alright, we'll stick some sulfuric acid in there. Alright, now, this first step is basically the same. We have to do that preparatory step where we turn the OH into water. It's going to grab a proton from your sulfuric acid. Alright, to give you that. Now, the difference between the E1 mechanism and the E2 mechanism here is that, just like with alkyl halides, in the first order mechanism, we form a carbocation. Alright, so your leaving group here, it's going to leave before your base comes in and takes your beta hydrogen. So it's going to form a C+. Alright? And then your base comes in, and our base, just like before, is going to be our leftovers from the acid, so HSO4 minus. Alright, here's a beta hydrogen right here we can target. You can grab that beta hydrogen. These electrons can fall into place, bond with that positive carbon, and voila, you've got an alkene. Not too bad, right? Now, what's one thing we haven't thought of, or one thing we haven't accounted for yet? Yeah, if you look closely, we have more than one type of beta hydrogen, right? Yeah. We also have beta carbons here and here. Now, these two are exactly the same as each other, so we'll just pick one of them to work with. But it's definitely different from that one. All right? So that means it's also possible, instead of plucking one of those, plucking the beta hydrogen that we did in the representative mechanism, we could have also targeted one of the other ones. So we could have also made this alkene as well, and we do. we make both of them. Just like before, we can identify major and minors. This one's more substituted, so it's going to be the major product. All right. So always be sure to look for possible multiple types of beta hydrogens. All right, let's do another one. Come on. There we go. Got a little delay there, a little lag. All right. Okay, let's take one like this. Right, you treat it the same way. Grab a proton from your acid. Gives you water. Water leaves. It leaves us a nice tertiary carbocation. All right. So again, we can look for different types of beta hydrogen here. I think in this case you'll see we actually have two different types. All right. One way we could go about it is to lose one from here, so I'll draw a representative mechanism. So we could get that. That's one of them. We also have that methyl group hanging down that can act as a beta hydrogen. So we could also get this. Am I missing anything? Absolutely. I'm assuming you're right, by the way, whenever I do this. I feel like kind of like Dora the Explorer. If you look at this one right here, you'll notice that we actually have a stereoisomer. We have an E stereoisomer. We can also get the Z version as well. So we would actually get 3 products. All right. So yeah, you can see that the primary ones are definitely going to be a bit more complicated. For one reason, because you can get multiple beta hydrogens and stereoisomers. They're also going to be more complicated for a new insidious reason that I haven't talked about before. This is going to be something that you always have to account for whenever... Whoa, okay, I don't know what happened there. Whenever you have a carbocation. And it's really annoying, but it's definitely going to be part of your thought process from now on. That is looking for the dreaded carbocation rearrangement. Dun dun dun. As this wasn't complicated enough, we got to worry about ions rearranging themselves. Unfortunately, we do. All right. Let me give you some background here. Remember, if you remember back when I told you that carbocations existed in a certain hierarchy of stabilities, right? Tertiaries were the most stable, followed by secondaries, and then primaries were very, very unstable. Basically, a rearrangement happens when a certain type of carbocation is formed, and for lack of a better way of wording it, it sees an opportunity to sort of undergo an internal rearrangement into a more stable type. At this point, for you guys, that's basically going to mean a secondary carbocation rearranges to a tertiary. All right? It can do so in a couple of different ways. All right, let me give you an example. Let's say we had this. All right, we're going to start off the standard way. We grab our hydrogen from the acid, blah, blah, blah. We make water. It leaves, blah, blah, blah. And we make a carbocation. All right, this is where things get a little different. What type of carbocation is this? Hopefully you guys can recognize that it's a secondary. All right, what can happen here is that if there are certain groups on adjacent carbons that have the ability to sort of rearrange themselves into forming a tertiary, it will. There's two different ways this can happen. The first is something like this. If you look at this carbon on the left, all right, I'm going to draw everything on it. It's got two methyl groups and an H. It is possible, very possible, for this H minus, not just the H, but the H with the electrons, the H minus, to detach itself from that carbon and hop over here. All right? Since you're adding H minus to that positive charge, that carbon goes neutral, you're taking electrons away from the adjacent carbon, so it now becomes positive. That is a carbocation rearrangement. That type is called a 1,2 hydride shift. And it's called hydride shift because H minus, a negative hydrogen, is called a hydride. All right? So basically you have a hydride that hops over from an adjacent carbon to satisfy the positive charge, and in the process it makes a new positive charge at a tertiary carbon. That is sneaky, and that is insidious, and unfortunately that does happen, right? It happens pretty reliably too. It's not unpredictable. You just have to remember to look for it. Now that we've had our most stable carbocation, now we can proceed with things business as usual, right? We can look for beta hydrogens, right? So a good representative mechanism would be to go after this one, grab a beta hydrogen, electrons swoop in, and you can make that alkene. Do we have any other beta hydrogens we could have targeted instead? Of course we do. We could have gone after one of the methyl groups. So this one actually has a couple of different products. Alright, so that is one type of rearrangement. There is one other type that we can have. Let's say we had something like this. Well, let's tweak that one a little bit. Let's say, and I'm going to skip ahead a little bit. I'm going to skip ahead to the middle of the mechanism, because I think you guys sort of get the first part of this pretty well by now, hopefully. Let's say, the adjacent carbon had an extra methyl group, and we had this. All right. Now, we can't do a hydride shift because that adjacent carbon on the left doesn't have any H's, right? However, it's not just H minuses that can move. You can move alkyl groups as well. You can move R minuses. So this CH3 minus could also hop over to form a more stable carbocation at this carbon, and now this carbon would be neutral and have another methyl group. This is called a 1,2 alkyl shift. And you can do this with methyl groups, you can do it with ethyl groups, you can do it with isopropyl, you can do it with whatever. All right. In general, smaller groups are easier to shift. So for example, if you had to choose, like, okay, am I going to switch over a methyl group or am I going to shift over an ethyl group, it'd be easier to shift the methyl group. All right. That's why H minus is, and also, if you have a choice between an H minus, a hydride shift, or an alkyl shift, it'll always be the hydride. But it is certainly possible to do these. And, since we can't do a hydride, we can absolutely do an alkyl shift here. So, if we were to go forward with the reaction from here on out, we'd approach it the same way. Look for beta hydrogens, so you could form this product. You could also form this product. Sneaky, sneaky. It's one of the most annoying things to have happen to you when you're predicting a product, but it's something you absolutely have to look out for. Unfortunately, this is something you have to look out for in any mechanism that produces a carbocation, even the mechanisms from chapter 7 and 8. I debated whether I should go over C plus rearrangements in chapters 7 and 8. The reason I didn't is because the book doesn't discuss them either. So I didn't want to get too disconnected from the book. The book introduces them in chapter 9. But be aware, they can also happen with the chapter 7, chapter 8 reactions. Yeah. For example, I'll show you one. Going back to this, remember what we said. With alkyl halides, anytime you have an S in one, you always get an E1 as well. So keep that in mind. So if we're going back to this, the Cl minus leaves. You get a secondary C plus. You can absolutely have a hydride shift here from this carbon. To give you a carbocation there. And then from there on out, you could apply the rest of your mechanisms. I'm not going to go over them. Hopefully you know them by now. But you could get your SN1 product. And you could get your E1 products as well. Yeah, so C plus rearrangements are a fact of life. It's something we have to deal with. Any reaction in which we make a carbocation. Okay? So be sure to look for it. Okay. So those are the two mechanisms for dehydration of alcohols using strong acid to make alkenes. There is another alternate way of doing this besides the strong acid method. Instead of using a strong acid, you can use a combination of POCl3 and pyridine. All right. POCl3 looks like this. Remember, phosphorus is one of those. I did a really bad job of drawing that bond, but hopefully you guys get the idea. Phosphorus is one of those atoms that's capable of expanding its octet, so that's POCl3. Pyridine is actually an aromatic molecule that looks a little bit different than what you're used to. We'll go over it in organic too, but that's pyridine. Now, just because I don't like drawing the structure of pyridine every time, a lot of times I'll be lazy and I'll just represent it as PYR. And that's probably what I'll do here. All right. This is an alternate way of doing a dehydration. It only works with primary and secondary alcohols. Doesn't work with tertiaries, and it's an E2 mechanism. All right. Some people like to use this method because they don't like to work with strong acids. I personally absolutely hate working with pyridine, but whatever you like. Let me show you how it works. Say we have a primary alcohol. All right, so what happens is, again, the first thing we got to do is we got to convert that OH from a bad leaving group into a good one. Now, usually what we do is we convert it into water. This is going to be a little bit different because we're not going to convert it into water. We're going to convert it into something else. All right. So instead of this alcohol group grabbing a proton, what's going to happen is instead it's going to nucleophilically attack that phosphorus. And in the process, it's going to cause a Cl minus to leave. So you get this, and then a pyridine comes in, acts as a base, and grabs this proton, and you get this. All right. And it's going to be this group, now that we've made, that's going to act as your leaving group. All right? This is going to leave, and what's going to happen is, again, we're going to target a beta hydrogen. We only have one type in this example. Another pyridine is going to come in. It's going to grab that H. These electrons will move into a double bond. So we end up with our alkene. We end up with POCl2. And we end up with another protonated pyridine. Okay? So this one's E2, works a lot differently than what we saw previously with the strong acids, but it's still a very, very viable method of making your alkene. Okay? All right. That is it for dehydrations. All right. I'm gonna keep going forward. Let's talk about some nucleophilic substitutions. One thing that we can do with alcohols is we can convert them to alkyl halides. We can make alkyl halides out of alcohols using a strong halogen acid, HX. And there's really only three of them that work: HCl, HBr, and HI. Why not HF? Well, HF's actually not a strong acid. It's a weak acid. So it only works with these. All right? But this is a good way to make alkyl halides. And you're going to see some similarities to what we saw with the E1 and E2 reactions. Just like with E2, SN2 only happens with primary alcohols, right? So also, just like the eliminations, these tend to be simpler. All right, so let's say you have something like this. All right. Again, we've got to get rid of that OH, and again, we've got to turn it into a good leaving group, right? So that's the purpose of using the acid here. Just like last time, we're going to grab a proton from that halogen acid, and we're going to use it to make water, which is a good leaving group. Now the difference is, since it's a halogen acid, we have a Br minus left behind. And this Br minus can actually act as a nucleophile. It's not a good one, but it's a better nucleophile than water is. So even though Br minus is pretty weak, it can attack this carbon, and it can knock off water. And Viola, you've got an alkyl bromide. Pretty cool, huh? And one thing, like I said, this is pretty simple. Since, it only works with primary alcohols, you don't really have to worry about stereochemistry here, right? Because you're never going to have a stereogenic center, unless you have isotopes, which is really, really rare. No carbocation, so you don't have to worry about rearrangements or anything. So it's very, very simple mechanism and reaction to remember. There is one exception here that is a little bit more complicated, and that's if you do this with HCl. Come on, go. Okay. Let's say you try to do the same reaction with HCl. If you did this, guess what would happen? Absolutely nothing. You'd get the big old NR. NR stands for no reaction. Why not? Well, Cl minus, out of all these, Cl minus, Br minus, or I minus, Cl minus is the weakest of the nucleophiles. In fact, it's so weak, it can't even knock off water as a leaving group. How sad is that, right? So, if you want to do this with HCl, you got to give it a little bit of help. You got to make an even better leaving group than water. So, you have to add some zinc dichloride, ZnCl2. And what we're going to see is something kind of similar to that whole reaction a few minutes ago with POCl3. The OH minus is going to nucleophilically attack your zinc, and it's going to bond to it. And it makes this. And it's this group collectively that acts as your leaving group. And that is a better leaving group than water. So good, in fact, that a Cl minus from your HCl can come in now and knock that off and make your alkyl chloride. Okay? So if you try to do this with HCl, just remember it's not going to work on its own. You got to give it some help. All right. All right, and that's really all about all there is to the SN2 reactions here. Now, of course, as we get into SN1, those are a little bit more complicated. SN1, just like E1, it works with secondary and tertiary alcohols. Okay? If you have something like this, it's pretty simple. We'll use HI since we haven't used it before. It'll start off exactly as you would suspect. We're going to grab a proton. We're going to make some water. Since this is SN1, remember we have to make a carbocation. So we make this. Let's do a check here. Get in the habit of doing this. What type of carbocation do we have here? We have a tertiary. If we have a tertiary, are we going to have a rearrangement? No way. So we're good as is. And then that I minus is left over. Bada boom, bada bing. It attacks. And you got your alkyl iodide. Easy peasy. Okay? Now, that being said, there is a little bit more nuance here. Since we can do this with secondary and tertiary alcohols, that means that we can absolutely have a case where we react at a stereogenic center. Let's say we have something like this. All right, so we have a stereogenic center there. Okay. We're going to add some HCl. We're going to lose our water to make our carbocation. And this one's going to be a tertiary carbocation again, so we don't have to worry about rearrangement. Now, remember, when you have a carbocation here, notice that methyl group, I didn't draw it as a wedge anymore, or a dash anymore, I drew it as a straight line. Don't forget, we have trigonal planar geometry here in the carbocation because it's sp2 hybridized. That means that Cl minus, when it attacks here, it can attack from the front side, or it can attack from the back side with equal success. And that means that we're going to get a mixture of stereoisomers, just like we did in the previous in chapter 7. So we could get this, and we could get this, and we do get both of them. All right, so you get a racemic mix. All right. Now the other thing that can complicate things, of course, and you probably are predicting this based off of what we just went over, we can always have the dreaded carbocation rearrangement as well. All right, so don't forget to look for that. Whoa, I'm getting serious lag here with my stylus. Go through the mechanism, grab the proton. Feel if I keep doing this with you, keep making you draw it, it's like that muscle memory, right? Sort of like from Karate Kid. Or, excuse me, Cobra Kai. You guys probably know Cobra Kai, but the show Cobra Kai better than the movie Karate Kid. Alright, so we have our secondary carbocation. We've seen before that we can have a rearrangement. Yeah, in fact, we saw this exact one in a previous example. The difference here is that instead of getting an elimination, our nucleophile attacks, and we get this product. Okay? So, yeah, be sure to look out for that carbocation rearrangement as well in these cases. Okay. That is how you use strong halogen acids to make alkyl halides from alcohols. All right. Now, just a couple more things before I quit here. Just like we saw, there was an alternative, right? In the last set of examples with eliminations, there was the POCl3 pyridine, alternative. There's a couple of alternatives for these reactions as well. All right. If you want to make an alkyl chloride, for example, one thing that you can do instead of using HCl is you can add something called thionyl chloride. Thionyl chloride is SOCl2, and it looks like this, in conjunction with pyridine. Okay? This is an alternative. It works, let's see, I'll write it down here. It works with primary and secondary alcohols, and it is SN2. All right, just like we saw before, this basically involves an alternative formation of an alternative leaving group that's not water. We do something else with it. All right, so this OH is going to nucleophilically attack your sulfur, kick off a Cl minus. And then your pyridine is going to come in, clean up that proton. To give you this. All right, so what we've done here is we've made it into a better leaving group, not water, but something else. That Cl minus that you kicked off of the SOCl2, it can come back, act as a nucleophile, and it'll cause this CO bond to break and sort of move over there. And then this kicks off. So your leaving group kind of decomposes a little bit on the way out. But you end up with your alkyl halide, your alkyl chloride, as well as SO2 and Cl minus as byproducts. Okay? Only works with primary secondaries. It's SN2, so you don't have to worry about rearrangements. All right, and that is specifically for alkyl chlorides. Don't try to use SOBr3, Br2 or anything like that. Also, try not to get the SOCl2 system mixed up with the POCl3. They look very similar, but they produce different things. All right, one last thing that you can do, again, just like with the last one, this works with primary and secondaries. And it's also going to be SN2. You can use PBr3, phosphorus tribromide, in order to make an alkyl bromide. Pretty similar. In fact, it's very similar to the last one, except a little bit simpler, actually. You can have a nucleophilic attack of the OH onto a phosphorus, which kicks off a Br minus. Right? One thing that's kind of nice about this one is you don't even need pyridine. Right? You can just go ahead, and this itself acts as the leaving group. That Br minus that you kicked off will act as the nucleophile to give you your alkyl bromide, and then this guy is a byproduct. So pretty simple method. All right, works very well. Okay, that is good. That is quite a bit of chemistry I've thrown at you right now. So as always, work through this, work some problems. Let me know if you have any questions. Until next time, I will talk to you later. Bye-bye.